Hi. As you said, I work for ArcSan. If anybody has any questions at all during the talk, just go ahead and speak up. Stop me if you have any questions about what's on the slide as well. This is a bit of a vague. I struggle a lot with this topic because, like, trying to find a name. But essentially, it's a lot of detection, which is the signature analysis part for malicious code or any code. And the software validation part is, hardening and resilience of binaries. So, get into this here. So, what is a signature? This is the biggest thing that I struggled with at first as I got into this research. And if you ever try to research signature analysis, if somebody comes up to you and says, "Do you want to do some research on this?" either know what they're talking about at first or say no, because there's way too many topics about signature analysis out there, and they're all completely different. One of the dictionaries online has a signature being a distinctive mark, characteristic, or sound indicating identity. If we're looking for malicious code, obviously a sound isn't going to help us a lot. Distinctive mark, maybe, but characteristic is what we really need to look for. So some kind of a behavior that is represented statically. So typically, signatures are signals when you think about computer systems. What you really need to think about in this is what a signature is. A signature is something that represents something else. And for the second point, we have a very specific definition that's related to the control flow of machine code. Because since this is binaries, we can't just look at the source code, right? Because we don't have the source code. And so, a signature for the purposes of code detection, malicious or not, then needs to be something representing a desired behavior through static analysis, as I said before. Therefore, defining a signature as a unique string of machine opcodes gets us what we want. Because a signature for malicious code is just code. So it's really pretty simple once you think about it, but it takes a while to come to that explanation. So a signature in this case would be, a push, move, move, sub, move, push, push, call. That is a signature. Because of the nature of machine code and its structure, searching for the string of instructions just in some binary is insufficient. You can't just load up, a hex dump and say, I'm going to look for these different code. Because you have jumps that go other places, you have other things that can affect it. So you really need control flow analysis in order to do this. If anyone isn't familiar with control flow, I'm going to go over this quickly. Control flow graphs and analysis. You can separate machine code into what's called basic blocks. So essentially, the idea, you can get into this second point as a definition, but the idea really is if you go into the basic block, you know for sure that you're going to execute every single instruction in that basic block before you leave it again. Right? So anything that jumps into it, that's going to start a basic block, and jumping out will end it. So, right. So anything that is executed prior to the current basic block, you call it X, would be a predecessor after a successor. You can treat the basic blocks as nodes and then create directed edges to create a control flow graph, which gives you a full idea of how exactly the program flows and where your code is going to go in any situation. That's a crazy looking control flow graph. Right. So it gives us the outline of every possible flow of execution. If you can apply a signature by checking the control flow graph, you can assure that you check every single possible way that code is going to be executed. Now you could have dead code that doesn't get linked, that doesn't get run, but if that's the case, it's not going to matter anyways. But this gives you every single possible way that could happen. Problems with control flow and signature analysis. No-op equivalent instructions and groups of instructions, aka instructions that don't do anything but are just there to trip up your signatures. You could have, push A, pop A, and that doesn't do anything, but it is not in the signature and therefore will trip it up. This can be alleviated, though, as we'll talk about later. The biggest problem, especially with control flow analysis, is this guy. This computed jump issues with control flow analysis. It's a big vicious circle, and if any of you guys know how to solve it, then you'd make lots of money because it's really, really complicated. And so essentially you need data flow analysis, which we'll talk about later as well, in order to solve the computed jump problem, which is, I'm not jumping to an address, I'm jumping to whatever's in this register plus some other register plus some memory number or something. So, unknown from the analysis, something that's only known at execution time. You need computed jump solutions to have full control flow analysis. However, you need control flow analysis for data flow analysis. So that's your vicious circle. There's no one has figured out how to solve it yet, but there are leaps being made. And you can kind of, if you know what the binaries are compiled from, you can make some good educated guesses. So how do we do malicious code detection? Create a list of signatures representing what you want, some virus, some this thing skips this code, whatever you got. Use signature analysis to detect it. We now know where the code is, but how can we analyze what it might affect, which is the next topic. Take a little side detour here. The signature analysis was my work specifically. The code slicing analysis is the work was done by the Wisconsin University, and you can go to this website and there's lots of cool, slideshows and different things that you can look at, and it's all everything that they've done, all the work that they've done is public. So, right, and the people who actually did the work on code slicing in my group were my colleagues Chris Staley and Joseph Bateman. So if you have any questions for me that I can't answer about it, I will redirect you to them and they'll be able to help you out. So, right, so what is code slicing? It's pretty cool, actually. This first bullet, a code analysis method to determine which parts of a program may affect, which is a backward slice or going backwards in the program, or be affected by a forward slice. Variable values at some point of interest. So you have your big executable, you've done all the things that you need to do. For code slicing, if you say, pick some random instruction, some add instruction, and you say, I want to do a forward slice on this add, then code slicing will precisely give you every single instruction that is affected by that add instruction in execution. So. Code slicing is an application of graph theory, and we all know that CS people love graphs and that there's nothing they can do to get away from them. So it starts with a control flow graph, which we've already looked at, which we just looked at for signature analysis. The next milestone is a program dependence graph. Code slicing for PDG is made up of flow dependence and control dependence graphs. So program dependence graph is a graph that's made up of two subgraphs. It allows intra-procedural slicing. So if you do a PDG on some function you write, printf or whatever, you wouldn't write that, but then you can figure out exactly which of these instructions will affect other instructions in that procedure, but you cannot do it throughout the whole program with the PDG only. First thing is flow dependence, which is sometimes called data dependence, which we talked about a little bit earlier as data flow analysis, which is problems with with computed jumps, right? if you need data flow analysis to solve computed jumps, but you can't. So this is sometimes called set use analysis or def use analysis, or definition use analysis. I've heard there is also another statement of def use analysis being related to test coverage, but this is not related to that. This is something different. So for every instruction in the procedure, a node is created. If a variable value is set in a given node, then an outage is created to the node containing the instructions in which the variable value is used. So directed edges are from set to use, which is the set use analysis. So a set would be, move 42 into AX. That you're setting AX to be something. A use is add BX to AX. As I say in this third bullet here, the use is actually also a set because once you're done with this instruction, the value of AX is changed. So that will stop the set from here, and we'll start a new set here. So if you wanted to do analysis on it, you don't have to go back to stuff that doesn't relate to it. All right. This is kind of related to the computed jumps thing, right? These are kinds of instructions that are generated by exception handlers and function pointers in C. So unfortunately, like I said before, you can do some interpolation and figure out exactly, what a compiler may be meaning by this if you know exactly where it was compiled from. But doing a general case does not work very well. Because data flow analysis does not know that this is actually this. It just knows that this is BX. Right. And I think I flipped these, but that's okay. So now control dependence. It's a graph that represents reachability within an application. Can you get something from something else? Will setting this value cause this, well, that's set use, but will that cause, an if statement to go into a different place? That's kind of reachability. So for every conditional statement, a node is created and a true out edge is added to instructions reachable only if the statement is true. The same is done for false. That's a little unnecessary in binary executables, right? Because there's no real false jumps. You just jump if it's true, and then it just falls through if it's not. So you can kind of think of it as the same thing. Because of the lack of structure, this can be very difficult to generate. It's nice in source code. You have nice little curly braces to show you exactly where things are happening and what code is affected by what code. But in binaries, you don't have that, and so you got to do a whole lot more finagling to get the analysis to be correct. Oh yes, and if you combine the CFG, the control flow graph, and the control dependence graph for the entire application, that can lead you to dead code analysis, which can show you where, hey, we can chop this code out of the binary, and because it will never be executed anyways, which is how compilers do a lot of their, some of their optimization. So if you combine the flow dependence and control dependence graphs, this is the program dependence graph for a procedure. So now we can do procedural slicing, slicing of different functions. However, this is not sufficient because we do need to know everything that is affected by the code that is detected. So it's not really worth just knowing what effects in the function it's in. System dependence graph is a combination of all the PDGs in an application. It's relatively simple. It makes a lot of sense. It's just kind of an extended PDG. You just create out edges from past parameters into the function where those parameters are used. So that's your set use. And out edges from the return value to where they're being used in the column. So, another note. In system dependence, it's also where you would you kind of need, because of the way global variables work, right, you need to essentially put them in every single program dependence graph that you have, because everything can use a global variable. Registers kind of that way as well. So there's a lot of trickiness to the binary side of this, but pretty cool. So a slicing example. We got a little application here that doesn't actually do anything. It's just some forced control flow. Moves down here. If it's less than, which it will be, jumps down here, sets it equal to, jumps back up, and then it's not less than, so it jumps to the end. So this is the flow dependence graph for this particular set of instructions. Now you can see, just from this is 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 nodes. You can kind of think of it as 9 nodes. And 1, 2, 3, 4, 5, 6, 7, 8, 9 edges. So there's, just for this tiny little program of 8 instructions, there's quite a bit to be had. So this takes up a lot of space in memory if you don't do it thinking to not take up space in memory. Right, so essentially this means taking a look at this node, right? You're moving 5 into AX, so it's set here, so you're using it here in this add. You're also using it in this compare. You're using it in this move here, which sets a new thing for BX. And so that's why BX is pointing here, and BX is pointing here. But BX from here is not pointing here because this overlaps, because BX gets reset here. So it does not point from there to there. I'm going a little fast on it. Is there any questions about anything? Sorry. No. Control dependence graphs. Right. So we have, this is a little simpler to read. Essentially every instruction that can be read, that can be gotten to from enter, just has a directed edge to it. And the biggest change here is this jump to my label, which is here. And that is only accessible if this is less, right? Oh, another thing to point out from the last graph, sorry. About this flag, right? Compares and jumps are 2 separate instructions in assembly language, or in machine code as well. So when you have a compare, what actually gets done is flags are set. And then those flags are checked whenever a jump is called. So you also need to keep track of the flags in assembly language. Yet another hurdle. So this is the PDG, which is just a combination of the flow dependence and control dependence graphs. The blue is from the control dependence. The black is from the flow dependence. Nothing much else to say there. So there are no other procedures in the example I gave, so it's already a system dependence graph because there is no other functions, there's nothing else, that's all there is. But if we replace add with a function procedure, then the SDG would be created as following. The call has directed edges to enter, push, and push, right? Because those are your parameters passed when you're using assembly. So this particular portion is just the PDG for the function of the add function, which uses add, but we won't talk about that. And then this is the return value that's being used in the caller. So you have a directed edge, from there to there, and the rest of this is just normal control dependence. So if we want to do a backward slice on add AX BX in this example, which is this particular node right here, first we follow the edge backwards, all the edges backwards, and then we are going to do in the next step, a backward slice of all the instructions that were reached from the previous step. So now we don't have anywhere else to go backwards from enter, so we can stop, and this is a code slice on a backward code slice of add ax bx from this example. And these are the, the bolded would be the actual slice itself. A forward slice is done exactly the same way, except you follow the edges forward instead of backwards. There's not a whole lot left to say about that. You just, go here, and then that gets you here, and you follow all the stuff around. This is your forward slice of the current example, and this is the part that's bolded would be what you get. So, problems with code slicing, and there's lots of them, as I've already talked about. But any error in analysis could quite possibly lead to a completely incorrect code slice, right? Because say you're missing an edge that goes to somewhere important that has like 15 edges in it or something, then you aren't going to get any of that information, and that's pretty much useless at that point. So, and the amount of space needed to store is very great. The following metrics are from my colleague's code. I mean, they were breaking the 2 gigabyte limit on a 1 meg size binary, trying to analyze it, and now it's down to 584 megs because the guy who was working on it is really stellar, and he knows how to do a lot of optimization. Used to take 20 minutes to do the analysis. Now it only takes about a minute. So it's possible, but it's quite a journey to get there. How can we use this? This is the researchy portion, right? It can actually be used to assist in signature analysis, even though we talked about that at first, because that was for the detection. It doesn't need code slicing after it. You could do the code slice before. So the problem that I was talking about with the no-op instructions, types of instruction sets, that can be alleviated here. We just run a code slice on the signature and find getting ahead of myself. Find possible signatures in the binary, starting and ending instructions, and then run your code slicer through there. And if you find anything that doesn't do anything, as in, if you do a code slice on it and it doesn't get anywhere outside of it, or it doesn't actually affect anything, then you can just strip that out as do nothing code and call it a no-op, right? And then that can be, you can pull that code out, then run your signature analyzer on it again with the actual signature analysis, and that will find that code because everything has been stripped out of it that doesn't do anything. The best and most desirable security is to have a resilient program from release, right? We don't, a lot of people want this. It's always going to be talked about. Just an important thing to think about. Code slicing can help. Run code slicing on a signature itself, not on the binary, but on the signature. Create possible out edges in the appropriate places, like if something is defined. For flow dependence, possible out edges could tell you which registers used in a certain way might be affected by a known security threat. Control dependence, the same thing, might be skipping licensing code or something like that. So, note, analyzing flow dependence and control dependence in a given way requires to not just know the algorithm for code slicing, but to truly understand what it represents. That also understands, in addition, you need an understanding of what the malicious code is intending to do. So this takes a lot of hand holding, but the analysis is there. So it gives some additional insight into the behavior of the malicious code represented by the signature. The behavior can be caught, by a separate thread or process, and which can alert the user or deal with or isolate whatever the problem is that you're running across. This is essentially what virus scanners do, right? But we're not talking about that specifically. They don't use code slicing, I know that for sure. And they don't. Their analysis is a bit different. So I went through that kind of quickly. I didn't. But is there any questions that anybody can answer? Any possible?
How do you handle packets?
Turn your mic on.
How do you handle like packet binaries?
Packet binaries?
Yeah, you write a packer that would pack the source code, and at runtime it would unpack the source code.
Like kind of managed code kind of stuff? Is that right? Or what?
No, like every guy that writes viruses writes a packer for their virus. So it's a little stuff that takes the binary, the code, it packs it into something that would trigger a different signature, and at runtime it unpacks that code and jumps there.
Oh, run. Okay, so you're talking about run. Well, that would be the idea of the runtime checker, like right, the running a separate thread or process, right, that does your signature analysis while the process is running. So
But are you gonna check at all times that the process is running?
just whenever the context is switched to that particular process or thread. Right?
Every time?
Yeah.
Every context switch, you're gonna do a check?
Anytime that the process is running. Yeah.
Yeah.
I mean, this is just researchy stuff, right? This hasn't actually. I don't have any proof of concepts or anything.
But what I'm saying is like all these things, all these signatures, like they've been trying to do it like 15 years and they haven't been able to come up with something that works actually. Like I don't know if you saw that in DEF CON there was a contest that if you could beat 13 antivirus companies, and it took 13 minutes for someone to beat them all.
Wow.
So.
Sorry. Sorry.
Thank you.